Good morning, students, and welcome to this morning's class. Today, we will be discussing with you a very two important approaches to obtaining the values or the measures of skewnesses, or the value of what of skewness. Do remember that in our previous class, we already had discussed the formula through which one can obtain the measure of skewness from a set of data. And then in that class, we gave the formula to be that skewness, let it be denoted by S, subscript what, subscript K, to stand for skewness. We gave the formula to be sum over the range of x minus x bar all raised to power 3 all over what? N minus 1 multiplied by standard deviation raised to power 3. This was the formula we gave with which one can obtain the value of skewness from a set of data. And then this n minus 1 is conditional. It depends on if our n is small or if our n is what is large. If our n is small, we make use of n minus 1. But if our n is large, we make use of what of n. That is to say, that somebody can equally say that skewness S subscript K can be given as sum over the range of x minus x bar all raised to power 3 all over what n multiplied by s raised to power 3. In this condition, our n is strictly less than what 30, but in this condition, our n is greater than or equal to what 30. Equally, in that class, we said that this formula alone, without this x raised to power 3, that is, the sum over the range of what x minus x bar all raised to power 3 all over n minus 1, or sum over the range of x minus x bar all raised to power 3 all over n. They are called the third moment about the mean. The third sample moment about the mean of the observation. This one is equally called the third sample moment about the mean x bar. And if you watch, what I have in the numerator here is this formula. And what I have in this numerator here, aside this from s raised to power 3, is this formula. And that is the reason why some people call the measure of skewness to be the third moment. To be the what? The third moment. However, in today's class, our emphasis will not be on obtaining the measure of skewness from a data set. We are going to look at obtaining a value of skewness from the approaches of Karl, Pearson, and Bowley's coefficient of skewness. So you permit me to clean here while we now discuss what we have here. Okay. Karl, Pearson, and Bowley said that the measure of skewness can equally be obtained from the following measures. 1, measures of central tendency. Measures of central tendencies. Okay? That it can equally be obtained from measures of dispersion. Measures of dispersion. And it can equally be obtained from what is called measures of partition. Measures of partition. Okay? And it can equally be obtained from what we call measures of moments. Measures of moments. Measures of moments. So what we're going to do here is, according to Karl Pearson, what measures are we going to use to obtain the measures of skewness, and what is the formula? According to Bowley's, what are we going to use to obtain the measures of what of skewness, and what is the formula? So we begin by, according to Karl Pearson, according to what? Karl Pearson, we are going to make use of the central tendencies and then the dispersion. And then according to Karl Pearson, Karl Pearson, okay, the coefficient of skewness, I will write it in full, the coefficient of skewness, coefficient of skewness, denoted by S subscript K, is given as S subscript K is equals mean minus mode all over standard deviation. Standard deviation. That is to say that the moment you know the value of the mean, mode, and the standard deviation from a data set, you can obtain the measure of a skewness according to Karl Pearson. And Karl Pearson is saying that the highest value that this coefficient of a variation or coefficient of skewness according to him can take is +3. And the least value it can take is -3. So according to Karl Pearson here, we are saying that -3 is less than or equal to S subscript K, which is less than or equal to what? Plus what? 3. This is the range of this estimator of Karl Pearson. Okay? However, it is important to note that in some data sets, there is no mode. Perhaps what we always say bimodal, mode and bimodal, in terms of the same set of observations having the same frequencies. So you cannot say that this is a particular data set with, or the particular data point with the highest occurrence. So in that case, it becomes difficult to say that the mode of this data set is this. And the man is saying that in a situation where the mode of the data set is given, that you can use this formula to arrive at the same thing. That you can say that my S subscript K will now be given as 3 into what? Mean minus median all over standard deviation. Standard deviation. According to him, these two formulas arrive at the same answer. Okay? They arrive at the same what? Answer. The essence of this formula is when the mode of the data set is not given. And then I want us to see something here quickly. What we are to see is this. Here is SK, here is SA. And it implies that this my S subscript K is equals S subscript K. How do I mean by this? That S subscript K here, where we are making use of the mode, is the same thing as S subscript K here, where we are making use of what? Of median. Because you can see there is a little adjustment here because of the presence of this word 3. And if this formula and this formula are the same thing, if you watch here, you find out that what I have at the denominator is standard deviation, and what I have at the denominator here is standard deviation. If this formula is equal to this formula, it implies that the numerator of this formula is equal to the numerator of this formula, and the denominator of this formula is equal to the denominator of this formula. How do I mean? Let me call this things up here. From this formula here, what I have is that my mean, what I have here is that my mean minus mode all over STD, standing as standard deviation, is equals, here is my 3, open a bracket, I have mean minus median. This is median all over STD. That's what I now have. This thing is a median, what I wrote here. Now, if you watch, the denominator here is STD, the denominator here is STD, standard deviation, standard deviation. And this standard deviation is equal to this standard deviation. Therefore, this numerator must be equal to this numerator. And in that case, one can therefore say that here you have that your mean minus mode is equal to 3 into mean minus median. See what we have arrived at. And then because of this formula, somebody can decide to give you 2 measures of central tendency and require you to find the other one. How do I mean? Mean, mode, and median are all measures of central tendency. So somebody can say, from this data set, or from a given data set, the mean is this and the median is this. Find the mode. Or it will tell you that then the mean is this, the mode is this, find the what, the median. You just need to play around this relationship here to be able to find the remaining value of the measure of a central tendency. As a quick recap, we are looking at a way we can obtain the measures of skewness according to Karl, Pearson, and then Bowley's coefficient of skewness. According to them, the measures of skewness can be obtained from measures of central tendency, measures of dispersion, measures of partition, and measures of what, of moment. But according to Karl Pearson, he is making use of measures of central tendency and dispersion. And then the formula is given as mean minus mode all over standard deviation, which he says that the highest value that this formula can have is +3. But the least value it can have is what, is -3. So the range of this estimator lies between -3 and then +3 inclusive. Then it's now saying that what in a situation where the mode of the data set is not given. If it is not given, we make use of what, of the median. But then there is a little adjustment here. So here what we have now becomes 3 into mean minus median all over standard deviation. And then because of this formula and this formula, we are trying to see the kind of relationship that exists between the 3 measures of central tendency, which are the mean, the median, and then the mode. The denominator here is standard deviation, the denominator here is standard deviation. The value of this SK here is the same thing with the values of this SK here. Therefore, the numerators here are the same thing. The numerator here is mean minus mode, here is mean minus mode. And then the numerator here is 3 into mean minus median, which is 3 into mean minus median. So it implies that what I have here and what I have here are the same thing. So one can then decide now to give you some measures of central tendency and require you to find the others. This is the formula you should be using to play around with that. Pay attention to this. So permit me to clean the board, then give you the measure or give you that of the Bowleys before we now take a real life example to work together. So permit me to clean here. Remember that mean mode is measure of central tendency. Remember that standard deviation is measures of dispersion. So in the Karl Pearson, the measures that he is using are measures of central tendency and dispersion. We want to go to Bowley's that pays attention to partition. Okay? Yes. According to Bowley, he said that the coefficient of what? Of skewness. Coefficient of skewness, which is S subscript K, is given as S subscript K is equals. We have what we call Q what 3 plus what? Q what 1 minus 2 Q what 2 all over Q what 3 minus Q 1. This is the formula for obtaining the coefficient of skewness according to Bowley's. And he said that the least value that this formula can take is minus 1. And then the highest value it can take is what? Is plus 1. So this becomes the range of the Bowley's coefficient of skewness. Okay? Then we now say where the Q3 is what we call the third quartile. Then our Q2 is what we call the second quartile. And we should remember that the second quartile is the same thing as median. This thing can be seen when we treated the measures of central tendency, even though we are going to look at measures of quartiles in a separate class. Then we now have that our Q1 is what we call the first quartile. So this is according to Bowley's. So what we are going to do is to quickly clean down the board and take a real life example to see how these things are done. The only thing we should remind ourselves to bear in mind is when we calculate the value of skewness and then the answer we get is 0, we now say that the data is neither skewed to the right nor to the left. Instead, the data is normal. However, when we calculate the value of skewness and the value is non-zero but is positive, we say that the data is skewed to the right. If we calculate it and then the value is non-zero but it is less than 0, we say that the data is skewed to the left. How do I mean by this? When we calculate S subscript K and the value becomes what? 0, we now say that our data set is normal. Our data set is what? Is normal. Okay? But when we calculate S subscript K and it becomes greater than what? 0, it means it is a positive quantity. And we now say data is skewed. Skewed data. To the right. But when we calculate and we have S subscript K, which becomes less than what? 0. Okay? We now know that our data is skewed to the what? Is also skewed, but is skewed to the left. So here we call skewed data. But this time around to the left. So we are going to take a question to illustrate all these things which we have seen. So permit me to quickly clean this. Okay? Always pay attention to this. Always pay attention to the range of a Karl Pearson, -3 to +3. Pay attention to this one, -1 to 1. Okay? Then equally remember these conditions. When SK is 0, normal. SK greater than 0, skewed to the right. SK less than 0, skewed to the what? To the left. Thank you very much. Permit me to clean it down and then we'll talk on that one. Okay, look at little question I have here. That little question I have is this. So I call it example 1. Example 1. We have a data set given to us this way. Okay. Here is my x. Here is my f. So I have here 1, 2, 3, 4, 5, and I have the sixth one. 6. The frequency of this one is 3. Here is 1. Here is 4. Here is what? 2. Here is 1. And here is 2. The question said here, obtain SQ, obtain SK according to Pearson. According to Pearson. Then also obtain SK according to Bowley. According to Bowley. So what we are going to quickly do is to remind ourselves the formula for Pearson. Pearson says, so as a way of solution, Pearson says that its own formula is S subscript K is given as what? Mean minus mode all over STD. This STD stands for standard deviation. So by implication, for me to calculate this, I need to get the mean, I need to get the mode, and I need to get the standard deviation. Okay? So for that reason, you can come and do something like this. You can come here and have your X, you have your F. You do something of this kind. Your X here is 1, here is 2, 3, 4, 5, 6. The frequencies are what? You have here 3, you have here 1, you have here 4, you have here what? 2, you have here 1, and you have here what? 2. Then you have something like this. So we now say here, we come here and say, but our mode equals. Remember that mode is defined as the data set with the highest frequency. So we come here, here is 4, which is the highest frequency. What data point has that 4? It is this 3 here. So the mode is equals what? 3. We have gotten the mode. So we now come here and we have something called fx. Fx now we are going to use this to multiply this. So 1 times 3 will give me 3. 2 times 1 will give me 2. 3 times 4 will give me what? 12. 4 times this will give me 8. 5 times 1 will give me 5. And this time this will give me 12. Then you underline so that you can sum. I summed this thing earlier and what I had was 13. I summed this thing earlier and what I had was 42. Here was 42. That was what I had earlier. Okay, so what are we now going to do? We now say therefore that my x bar, which is the mean, x bar, or let me put it this way, mean, which is x bar, is given as sum of f what x all over sum of f, which is given as sum of fx is 42. I have 42 all over. Then sum of f is what? Is 13. And what I had earlier when I divided this, I had it to be that this is 3.2308. This was the value. I have gotten this, I have gotten this, I have to get this. Okay? So the standard deviation here, or let me first of all begin with the variance. The variance S squared is given as sum of f x was squared minus sum of fx all raised to power what? 2 all over n all over what? N minus 1. I will explain this. This is of course a computational formula on how to get the variance. Okay? Here is fx squared. You must have squared your x before you use the frequency to multiply it. That is to say, if you come here, you have fx what squared, a column that talks on that. So here is my x. That x must be squared first. Here is my x. 1 squared is 1, multiplied by 3 is 3. Here we have 2 squared is what? 4, multiplied by 1 will equally give me 4. Here is my x. X squared here will give me what? 9. 3 squared is 9, times 4 will give me 36. Here is my x. X squared here means 4 squared, 16, times 2 will give me 30 what? 2. And here is my x. X squared here means 5 squared, which is 25, times 1 is what? 25. And here I have this one to be that this is 6 squared, which is 36, multiplied by 2, which is 70 what? 2. When I summed all of this earlier, what I had was 172. So in that case, you come here and then you now say that your x squared now is giving us the whole of this thing has become 172. You have 172 minus the whole of this fx was what you got earlier to be 42, and you have here to be 40 what? 2 all raised to power 2 all over. N here is standing as the total number of persons, which is sum of the frequencies. So it is 13. So you have here to be 13 all over. Here is 13 minus 1, 13 minus 1. Because I don't have the calculator and I cannot be switching over, writing on the board and pressing the calculator, when I evaluated this in earlier, the answer I had was, I had that this is 3.0256. And then we are talking about variance. So if you talk about the standard deviation, it is the square root of a variance. So we now say, therefore, our S alone, which is the square root of this variance, gave me 1.7394. This was the value I got there. So because of this value, please permit me to quickly clean here. So that I will be able to conclude this work. So let me clean here. Let me clean this place. Okay. So I will now come here and say therefore. Therefore, my S substitute K is giving us my mean is 3 points. This is 3.2308 minus. My mode is 3, so I have here to be 3 all over. My standard deviation is this, but it's going to, so I have my standard deviation, which is 1.7394. If you set this minus 3, you'll be able to have 0.2308 all over 1.7394. The good news here is that if you divide this and this, it lies between minus 3 and 3, number 1. Number 2, this value here is positive because the numerator is not negative and the denominator is not negative. Therefore, it is going to give us a situation whereby our SK is greater than what? 0. Because this thing cannot be 0. It is greater than 0. And because of that, we quickly say that this our data set is skewed to the right. It is what? Skewed to the what? To the right. Because the value of the coefficient of skewness is greater than 0. That is how to go about finding this of according to Karl Pearson. We are equally going to show you how you can get a value for Bowley. But then we show you that value, we now have a separate class teaching students on how to calculate quartile from an array of a data set and from an ungrouped frequency table. So in this class, we are just going to mention the values that we got for Q1, Q2, and Q3, while we have a separate class discussing how to arrive at these values, because doing it in this class will actually make this class to be too voluminous. So permit me to clean all of these things. Okay, permit me. You have seen what we have done here. Okay, remember that according to Bowley said that we have that S subscript K is given as, we have Q3 plus Q1 minus 2Q what 2 all over Q3 minus Q1. That is how Bowley said. So I am quickly going to say where, I will not say where, because already we have got their values. We say where, okay, we obtained their values earlier and then we reported. Okay? Yes. We now say where our Q1 was gotten to be. Our Q1 is, the value we got was okay, 1.5. Then our Q2, which of course is the median, the value we got was 3, and our Q3, the value we got was 4.5. We are going to have a class teaching how to arrive at these values. Permit me to remove what came up on the screen. So we now say, therefore, our S subscript K is given as, my Q3 is 4.5 plus, my Q1 is 1.5 minus 2, then my Q2 is this 3, close it all over. My Q3 is what? 4.5, and then my Q1 is 1.5. So the moment you evaluate this, that becomes the coefficient of skewness according to Bowley's, or Bowley's coefficient of skewness. Okay? So if you have any question or any concern to raise based on what we have discussed far, feel free to drop your question in the comment section. Surely we are going to address it once we come across it. Don't forget to subscribe to our YouTube channel, like and share our videos, and surely you are going to benefit maximally from our consistent classes. Thank you very much.